Okay, here we go. You've just done a bunch of discovery, exploration about transformations of sinusoidal functions, and now we're into 5.4. We're going to take some notes, graphing and modeling sinusoidal functions. So we can use the sine or cosine function to model real-world situations by applying the necessary transformations to the amplitude, period, vertical shift, and phase shift. For example, tides in the ocean can be modeled using a sine function with a period length of about 12 hours. So we're taking our standard y equals sine of x, doing a bunch of stuff to it, transforming it, in order to model real-world situations, like the carousel going around, or like the phases of the moon, or like tides. Okay? Example 1, characteristics of a sinusoidal function from an equation. An engineer uses the function y equals 3 times the cos of 2 times x minus 5 plus 4 to model the vertical position. Try to pay attention to what he's actually doing. He's modeling the vertical position y in meters of a rod in a machine x seconds after the machine started. So there's a rod in a machine, and it's, I'm going to guess, going around and around and around and around, and he's testing the vertical height of it. So we've kind of got this picture of this rod, R, going around and around and around, and over time, which is going to be our horizontal axis, okay, it's going to have a vertical displacement. So it's going to go either up or down. So it's actually going to look like, this is what the wave will look like. Yeah?
Why is that going under?
So it's time over time. As it goes around, it's going up and down and up and down and up and down. Okay? So this just tells us the position, the vertical position of this rod over time. Maybe at 5 seconds it's at the top, and at 10 seconds it's at the bottom, and at 15 seconds it's at the top again. We don't know. So I'm going to take those numbers away, but this is essentially what's happening. Okay? What are we going to do? We need to identify the amplitude, the period, the phase shift, and the vertical shift of the function that's modeling the position of the rod. Okay? So all we have to do is compare the function that we've been given, which is y equals 3 cos 2 x minus 5 plus 4. We're just comparing that to our general form with amplitude out front, k x minus d plus c. And we're just identifying the parameters. So, what is a in our function? A is 3. What is k in our function? K is 2. D x minus d, x minus 5. D is 5.
What if there's a 2 in front of the x? Does that change the...
If there were a value inside this bracket,
Yep.
we'd have to factor it out.
Oh,
Okay, we will come to examples like that probably. If in order for it to represent k, it has to be outside the bracket, or you could have, like, if there was no d, it could just be like 2x.
but like on the example it says 2x. And then some number, and then if it's negative, like 30 degrees or something.
Like this.
Yeah, in the dark.
If this happened, then we would have to factor out, and it would be like that. Okay? I don't know if we're going to get to that. Let's just carry on with what we have. C. The value of C is 4. Okay. Here we go. So A, that means the amplitude is 3, and he's measuring in meters. So this tells us that the amplitude is 3 meters. So that means from the rest position wherever that is. This rod is gonna travel up 3 meters, and then back to the rest position, and then down 3 meters, and then back to the rest position, and then up 3 meters. Okay, so you're already kind of knowing the range, a little bit of information for the range as well. Let's determine the period length. How do we determine the period length? So the normal period length of the cosine function is what? How long does it take for the function to repeat itself? 360 degrees. Okay, so we've got 360 over k, which is 360 over 2, which is 180. So the period length is 180. That means it's going to complete 2 cycles over 360 degrees. And actually, we're not talking about degrees at all, are we? We're talking about time measured in seconds. So the period length is 180 seconds, which is how long? In minutes. 3 minutes. Excellent. Here we go. Let's talk about phase shift.
So that's the thing to go once around.
Pardon?
Thing to go once around.
For it to repeat itself is going to, take 180 seconds. Yes. Okay. Phase shift is determined by what parameter? A, K, D, or C?
Is that
Phase shift is horizontal. D. So what's going to happen to this thing? Yeah, which way? Right. So it's going to move, the phase shift is right 5. Now what's my units of measurement on my horizontal axis? Seconds. So it's going to move to the right 5 seconds. And our vertical shift is what? 4. What units are we measuring in our vertical axis in this case? Look at the problem again. Meters. Up or down? 4 meters up because it's positive. Okay, so A said, what are the amplitudes, period, phase shift, vertical shift of the position function? That's what we've done now. Okay, we did it by first identifying our values of our parameters in our general form, and then kind of translating that into, okay, what does it actually mean? Amplitude comes from A, period is 360 over K, phase shift is D, and vertical shift is C, making sure we had our correct units. Okay? Notice amplitude deals with the vertical, so it's measured in meters, along with vertical shift. And phase shift and period both have to do with horizontal axis. That's why they're measured in time. They're measured in seconds. Okay? B says, what are the lowest and highest vertical positions that the rod reaches? That's the same question as what are the max and the min? Okay? There's a couple different ways to think about it. Let's maybe just do A, B. You can do it in your head pretty simply, but just a couple notes that I'm going to take if you can have some space here. We'll take a couple notes. The basic cosine curve has min of -1. So in this case, if we have an amplitude of 3, how would I say this? Our function would have min of -3 because A equals 3. Now what else is happening to it? Because it's not just stretching. What else happened to it? What else is going to change the range of our function? Somebody say something. What is c doing to our function? Moving it up 4 units. Our function also shifts up 4 units. Therefore, minimum equals -3 plus 4 equals 1. And by the same logic, take a few seconds, try and figure out the new maximum. Slide, any idea? So the original maximum is 1. We stretch it by 3 and then move it up 4. Well, we got 1 times 3 is 3. Yep, vertical. A is going to give it a vertical stretch. So we're going to vertically stretch it up to 3, and then we're going to add 4. Okay? So the min is 1 meter, the max is 7 meters. What's our rest? So the rest would be 4. All that happened, you can get that right from here, right? If we move it up 4, then the rest is going to be 4. Another way to think about it is if the min is 1 and the max is 7, they have the exact same amplitude, top and bottom of the rest, then 4 must be in between that. 7 plus 1 divided by 2. Rest equals 4 meters. C. C says, use an extended table of values to graph the function from 0 to 360. Okay? So I'm going to clear off this. We'll leave that stuff up there. In your extended table of values, basically you're starting with y equals the cosine of x, and you're filling in the x and y values for cosine of x where there are no transformations happening yet. So what are those values? Let's start with 0, and what are some of the key points along that cosine? Cosine starts at 1, right? A max of 1. Should be fairly familiar with the cosine wave at this point. How long does it take to reach its minimum, or to reach rest, to reach 0? Okay, so if you're looking at the front cover of your book, you can see that the cosine wave, the gray one, crosses the x-axis at 90. So at 90 degrees, it has a value of 0. When does it hit its minimum? At 180 degrees, it's worth -1. Then it crosses the x-axis again at 270. So it's got a y value of 0 at 270. And then it hits its max again at 360, having completed 1 full rotation. Okay? We could... Do you have... is that the full chart, or do you have more space?
We have space on the side.
1, 2, 3, 4. Yeah, but that fills out the chart, right, to the bottom? Okay. So now, same as before, we're talking about stretch, reflection, translation, stretch, reflection, translation. So this is our extended table of values. Okay, we're going to use our parameters and see what's happening to each of these values. Well, let's talk vertical first. We said there's a vertical stretch by a factor of 3. So that's going to take all these y values and multiply them by 3. Okay? Is there any vertical reflection? No. A would have to be negative for that. Let's look at the translation on the y values. Every single y value is going to be added 4 to it. It's going to move up 4. So we're going to end up here. 3 plus 4 is 7. 0 plus 4 is 4. Negative 3 plus 4 is 1. And work down the chart. Now over to our x coordinates. This one's a little bit trickier. Okay? K is 2. So that is a horizontal compression by a factor of 1 over 2. So all of our x coordinates, you can think of it here, everything along our x is going to get pulled toward the y by a factor of 1/2. So if we had, for instance, a point right here, it's not going to be there anymore, it's going to be here. If we had a point here, it's going to be here. Okay, everything is getting squished in toward the y-axis, which means we're just cutting all of these numbers in half. 0, half of 90 is 45, half of 180 is 90, half of 270 is 135, half of 360 is 180. And now, so we've taken care of K, our stretch compression factor. Is there a reflection, a horizontal reflection? No. So we're looking for our transformations, which is the parameter D, which we said is going to move everything to the right 5. So we're just adding 5 to all of our values. So instead of 0, the x value is going to be 5. Instead of 45, it's going to be 50. Instead of 90, it's 95. 140. 185. Pardon? I can't hear what you're saying. This is the standard cosine function. These are the points that are on the plain old y equals cosine of x. And these indicate the coordinates of the point on our new function after we've done our transformations. Yeah, so what we have on our graph, instead of going through 0, 1, it's going to go through 5, 7. It's going to go through 54. It's going to go through 95, 1. It's going to go through 144. And it's going to go through 185, 7. Okay? So with that information, we should be able to graph it. Okay? Again, there's a couple different ways to graph it. This is using an extended table of values. Now we have our points. You can plot them on your grid there after you draw it. And maybe what we'll do also is we'll draw the original as well. Okay? So on yours, and I can do it with you. Use black to draw your axes. You know what? I'm just going to do it on my book. Okay, so the original cosine function goes through the point 0, 1. It goes through 90, 0. And I'm actually going to stretch this out a bit. I'm going to say 90, 180, 270, 360. So here's my regular. So there's cosine of x, y equals cosine of x. Okay, this is 360, 180, 90, 270. And now for our new one, we can plot our new points. We're going through 5, 7, which is, I don't know, really close to here. 5, 7, which is way up here, actually. 1, 2, 3, 4, 5, 6. 2, 3, 4, 5, 6, 7. I didn't leave myself enough space, that's for sure. Maybe I'll just erase my table. I don't need it anymore. 54. 50 is right about here. Up to 4. 7, 6, 5, 4. 95, 1. That's going to be its min. And then it's back up to its rest position at 140 degrees. Push that up a bit. And then back to its max at 185. And that's one cycle. And then we would need to repeat that. We need to repeat that cycle. So here I'm adding from 185 to 370. No, 185. Period length is 180, so 365 will be my next max. My next min will be at, or my next rest went from 50 to 140, would be 230.
The first 5, 7. Where's your?
My 5, 7 is right up here. And my rest was from 230, and then at 90 more, so 310. Be back at its rest, and its minimum will be 95 plus 180, 275. There-ish. And there's a graph of the curve of the function y equals 3 times the cosine of 2 x minus 5 plus 4. 2 cycles within 360, but it's also shifted to the right 5 units. And that's how to sketch a graph using your extended table of values. Just plot your points and draw a gentle curve. Okay, while we're here, let's quick run through just what are the domain and range of each of these functions. Okay, so the blue guy, our original cosine of x, what's the domain? The set of values of x that are used in the function.
Unlimited.
X belongs to the set of real numbers. Okay, get that language, please. What are the restrictions on y? What's the max? What's the min? Okay. So would you say that y is always in between -1 and 1?
Yes.
Okay. Be confident.
Wouldn't it be t this time?
This is vertical displacement. Time is domain, but we just use x and y because it's easier. Okay, what about our new one that we made? What's the red domain?
Let's do the set of real numbers.
X belongs to the set of real numbers. And the range? What's the minimum? What's the maximum? So is y always in between 1 and 7? Yes, it is. Okay. Okay, example 2, sketching again. Consider the function g of x, which equals 4 times the sine of 3x plus 1. Describe the transformations that must be applied to the function f of x equals sine x to obtain the new graph of g of x. Okay? So again, in this one we just have to describe the transformations that are happening. So I would right away again rewrite my new equation. 4 times the sine of 3x plus 1. I'd identify the parameters. So what's a?
4.
Therefore, amplitude is 4. So what does that mean when we're graphing? Or when we're transforming a graph? What's the language that we would use?
Stretch by a factor of 4.
Vertical stretch by a factor of 4. What is k?
3
K is 3, which tells us,
is a horizontal portion.
yep, horizontal compression by a factor of 1/3. Why did I leave this blank?
Because it's the same.
What's the period length? 360 over k. D. Is there a phase shift here? Is anything in brackets with the x? Nope. So D is 0. No phase shift. And C,
1.
therefore,
There's a vertical shift. Yes.
keep going.
Translated upward.
Good. So we've described the transformations to the graph. Okay? B. State the domain and range of g of x. Okay? Let's maybe do a little bit of a comparative thing here. So here's A. B. Y equals sine of x has a domain and a range. And y equals 4 times the sine of 3x plus 1 has a domain and range. Sine of x, what's the domain? X belongs to the set of real numbers. Range?
Stay within 0 and 1.
So y is greater than or equal to -1 and less than or equal to 1. Okay? Let's look over at our new one. The domain is pretty straightforward. What's the domain of our new graph?
It's mostly the set of real numbers.
Yeah, still no restrictions on x. As long as x isn't in the denominator, you're pretty much good to go with the set of real numbers. The range used to be a minimum of -1, but now we have a vertical stretch of 4, and then we're going to move the whole thing up 1. So what's our new minimum? At -1, we're going to stretch it by 4, and then move it up 1. Yeah? That's your new minimum?
Would it be negative 4? Because
Mm-hmm. So we stretched negative 1 times 4, which is negative 4, and then we move the whole thing up 1.
makes sense.
Maximum, it was 1. What's your new maximum going to be? You're going to stretch it by 4. So your new max will be 4, and then you're going to move the whole thing up 1. Okay? So another thing we just kind of reviewed incidentally is the fact that you deal with the stretch, compressions, reflections first, then you deal with the transformations, the shifts. Okay? So there we have our new range. C. Modify the equation of g of x, so that's the new one that they gave us in example 2, to include a phase shift of 30 degrees to the right, and call that equation h of k. So C, we have g of x, it's right here. Okay? How are we going to include a phase shift of 30 degrees? What parameter here is going to change? D is going to change. And what's the value of D going to be if we're going 30 degrees to the right? So D is 30. So if we were going to rewrite our equation for h of x, A would not change. It's 4 times the sine. And now this is where we get a little bit of a change because we're going to need a square bracket here. Because we have something happening to x. We're shifting x over. X minus 30 is still plus 1. Well, that was pretty good. Let's graph it. So extended table of values again, using our new h of x. Okay, we're going to graph h of x. I'm going to leave it there so that I can copy it up here. H of x equals 4 times the sine of 3 x minus 30 plus 1. We're going to start with the x and y values of y equals sine of x. Okay? Y equals sine of x goes through 0, 0. And then what happens to it? Probably thinking about what happens at 90, what happens at 180, what happens at 270, and what happens at 360. And now we're extending this. We've got our stretch, compression, then reflection, then transformations. We've got stretch, compression, then reflection, then transformations. Doesn't matter which side you start on. Let's go vertical first. We have a vertical stretch by a factor of 4. So write your new y values. There is no vertical reflection. There is a vertical translation of up 1. Now we can look over to our x coordinates, our horizontals. There's going to be a compression by a factor of 1/3. Okay, so 0, 0 is not going to move. Compression by a factor of 1/3, that means 90 becomes 30, 180 becomes 60, right? 270 becomes 90, 360 becomes 120. No horizontal reflection, and then we're moving to the right 30. So 0 becomes 30, 30 becomes 60, 90 becomes 60 becomes 90, 90 becomes 120, and 120 becomes 150. Which gives us our new coordinates of 31, 65, 91, 120, -3, and 151. And go ahead and draw a smooth curve through those points and extend it also to 360 degrees. Extend it, your graph, to 360 degrees. Mine's pretty sloppy. Anyway, should be able to plot your points. And if you're not sure how to start over in this area, okay, this point right here is like it was going through 0, 0. The other thing you can do is you can kind of trace this backwards. You can say, okay, where is it going to be at -3 again? Well, it's at -3 at 120, and a full cycle is 120, right? Because it's doing 3 cycles within 360. So we know it's actually going to cross here. And same thing, you can keep going all the way to 360. Going to have a min at 0 at 120. That means it's going to have another min at 240 and another min at 360. It's crossing the axis at, or it's here at 90, 150. We add 120 to each of these values. So we'd be at 151, and we'd be at 210, 1. And then we have the max here. Am I messing up?
Where's the dot now?
My min? Min should be at 360. So this should be 5 going all the way across. This should be -3 going all the way across. And the rest should be at 1 going all the way across. if we were going to draw the original sine function on here, it would look like this. It would have a max at 90. It would cross the x-axis at 180. It'd have a min at 270, and it'd come back up at 360. It would look like this. So actually, my scale is a bit deceiving, although accurate. Our red one is actually quite squished in comparison to the original blue one. And just so we're remembering to be consistent, we always label our graphs. So this is h of x, which equals 4 times the sine of 3 times x minus 30 plus 1. Example 3. Represent a sinusoidal function given its properties. So we have a sinusoidal function, which just means that it's a wave function that repeats itself. Okay, a cosine function is a sinusoidal function. Okay, sine and cosine are both sinusoidal functions. They're both wave functions that repeat themselves. This one has, and we're just going to write down the parameters as they come. So in A, we've got an amplitude of 3 units. So A is 3. We've got a period of 180 degrees. Okay, so if the period equals 180, that's not K, right? Remember, period is 360 over K. And we're told that the period is 180. So we have 180 equals 360 over K. So K is 360 over 180, which equals 2. And if you're not sure how I did that, there's 2 ways. Algebraically, you would multiply both sides by K, and then you divide both sides by 180. In my mind, I just try to make a division triangle. If 360 is on top, and 180 is here, and K is here, and 180 equals 360 over K, then K must equal 360 over 180, which is 2. Okay, what else do they tell us? They tell us that the maximum is at 0, 5. There's a maximum at 0, 5. Okay, so when x equals 0, cosine of x equals 5. Okay, why is that helpful? Well, we know where the cosine function usually has its max. It usually has its max at 0, 1. So this is actually nice. This tells us it hasn't moved left or right, because the maximum is still happening at x equals 0. It's still happening on the y-axis. So that's nice to know. The amplitude would have placed the max at positive 3, but now we're told that it's actually at positive 5. So what's happened here? We've stretched it by 3, but the max is at positive 5. So what other parameters are we missing here? We'll talk about D again in a second. But what's C? If you have a stretch of 3, Vlad, I would typically put the max at 3, right? But it's not at 3, it's at positive 5. So what else happened? It shifted up 2. So C is positive 2. Okay, I'll re-say how we know D is 0. Okay, there is no phase shift here, because cosine always has its max at x equals 0. That's how cosine is, unless you shift it. Well, here the max is still at x equals 0, so it hasn't shifted left or right at all. Okay, so our new equation as a cosine function is f of x equals, it's an a of 3 times the cosine has a k of 2 has no d, so it's just the cosine of 2x plus 2. Okay, identify the parameters, get your a, k, d, c, and then plug them into the equation where they go. Now we were asked to do it in two different ways. So we did it using a cosine function, okay? So if we just pay attention for a second, this is using cosine function. Okay? We're going to do the same thing, but we're going to do it using a sine function. Now, cosine function in this case is easier. Why? Why is the cosine going to be easier? There's no phase shift with cosine. Okay, we didn't have to move it left and right. The max of cosine is always at x equals 0, and it was again in this example. So sine is going to be a little bit more difficult, but we're going to use the exact same values here for a, k, and c. Right? Nothing has changed. It's still going to have an amplitude of 3. It's going to have a period of 180, which gives it a k value of 2. And we'll put in c is also going to be 2 again. But now we need a bit of thinking to figure out what the value of d is going to be. Okay? So we need to apply the appropriate phase shift to bring the maximum to 0, 5. So if we're thinking about sine, I'll just do a quick sketch here. We've got sine, it's been stretched up times by 3, and a vertical shift up of 2. So it's up here at positive 5, 0, but sine curve doesn't have a maximum at 0. The sine curve is typically goes through 0, 0, and is on its way up. And it hits its max later. It hits its max after 1/4 of a period length. So in this case, it's actually going to come through. It's going to come here instead of being moved just up from 0, 2. How can I explain that? So it would come up through 0, 2, and it would reach its max there after 1/4 of a period length. So where does the max normally occur for the sine function? Okay, yes, so the maximum value is normally 1. It's not going to be any more because we've already stretched it and moved it up. But where along the x-axis does it usually hit its max? Usually hits at 90, okay? So now we're going to say instead of it hitting at 90, we need it to hit at 0. So which way are we going to move this guy? Well, maybe I should restart one more thing. It normally hits at 90. Then we are, because k is 2, we're squishing it all. So it's actually going to hit at 45. And we don't actually want it to hit at 45. We want it to hit at 0. There we go. That's better. Now you should know how far do we have to move it.
45 degrees.
We have to move it 45 degrees, left or right, which makes D negative 45. Okay? Let me say that all again. So the maximum of the sine function normally occurs at 90 degrees, but the period in this case is 180, so all of these points are being compressed by a factor of a half. So 90 gets pulled into the y-axis just like all the other points along the curve, so that the max is now at 45. And then, in order to move the maximum to the y-axis, we need to apply a phase shift of 45 degrees to the left. So that gives us a new function. We'll call this one g of x of 3 times, and this time we had the sine function, 3 times, and we're going to need square brackets, k is 2, x plus 45, because it's x minus d, close those brackets, and we're still moving it up 2. Now, what is the only difference between the cosine function and the sine function? The only difference is the phase shift. Okay, in order to convert from cos to sine, we did a phase shift of a quarter of a period length to the left. Okay? In order to go from this function, this sine function, back to this cosine function, we would just do a quarter of a period length shift to the right. So we would be subtracting 45 from this, which would get us just 2x again. Okay? Somewhat complicated, but that's basically what you'll be practicing today, is converting back and forth, coming up with an equation from cosine to model the situation, and then coming up with a sine function to model the equation. Last example, example 4, determine a sinusoidal function given the graph. So we're given the picture of the graph, and we need to determine the equation that represents the graph. What should we do? What did we do in every single other problem so far? The parameters, right? So let's go ahead and look for its amplitude. Let's look for A, K, D, and C. Okay? So from the graph, we can't really directly see its amplitude because we notice that it's had a vertical shift done to it. But we can see its max and its min. Okay? So what is its max?
3.
So the max of 3, and it has a min of -5. So in order to find the amplitude, we take the max and we subtract the min. So you've got 3 minus -5 and divide it by 2. 3 plus 5 is 8, divided by 2 is 4. So A is 4.
Come to practice.
Yeah, come to practice. So all we have to do is count down 4 from the max, and we'll get the rest. Does that make sense? So the rest is 3, take away 4, the rest occurs at -1. And you can check the picture to see if that seems to make sense. Okay, you can draw a horizontal line through the point -1, a horizontal dotted line through the point -1. That's now our reference point. The equation of that line is y equals -1, which tells us what? What other parameter does that give us? Tells us how far it's shifted up or down, right? What's the vertical shift? Down 1, so C is -1. Okay? Now we can use either sine or cosine to construct a model for it. For this example, we'll use sine, okay? Because it seems to go through the point 0, -1, which is kind of what sine does, except it's going to be reflected, or shifted rather. We'll do a shift. So here we go. We're using sine. We're going to determine the start of the first sine wave to the right of the y-axis, moving along the horizontal. So we are determining the start of the first sine wave. Where does the first sine wave start? Which means basically, where is it? Sine normally does this at the start. It goes through the rest in a positive direction. where is that happening along the x-axis? It's not happening at 0, 0.
At 60 or no?
Yep, excellent. It's happening at 60. Okay? So instead of starting at 0, it's starting at 60. Which means what happened? It shifted to the right 60 degrees. Which tells us that D is 60. Okay? Good. The last thing then to double check for is K. So we want to follow that line. We started, so this is my horizontal line, y equals -1, and we crossed that rest point at 60. Where does it cross it again? Where does it complete one full rotation?
180.
Yep. So then one period length is 180 minus 60, which is 120. Okay? So if a period is 120, do you know off the top of your head what K must be? If not, then you can do it like this. You've got period equals 360 over K. 120 equals 360 over K. K equals 3. We have all our information. We've got amplitude. We've got C. We've got D. And we've got K. And we used a sine function. So let's call this thing, we can call it Y. Y equals 4 times the sine, square bracket, 3, x minus 60. Okay, if you're still having a hard time knowing that it's x minus 60, the standard form is x minus d. And d here is positive 60, so x minus positive 60 is x minus 60. And we're moving this thing down 1. And there you have it. Okay, you can always double check with Desmos as you're working through it. Your homework is at the bottom of the page, page 318, 1 through 13.
Would you request to do the